let's take a look at Millikan's oil drop experiment. So Robert Millikan was an American experimental physicist. He went to Oberlin, he was professor at the University of Chicago, and in the early 20th century, he did a series of experiments that collectively were known as Millikan's Oil Drop Experiment. And these experiments allowed him to determine, for the first time, the charge on an electron, which we now know is the fundamental charge, or elementary charge. And he later won a Nobel Prize for this, partially for his work with the photoelectric effect. Here's what the oil drop experiment did. So Millikan had a closed chamber, and inside of this chamber there were two plates, an upper plate and a lower plate, and those two plates could be charged, though in this first part of the experiment they're not charged. So Millikan sent in a cloud of small oil drops in between the plates, and each of these little oil drops was ionized or charged. Now, it doesn't really matter how they were charged. He could do it with friction by air or with X-rays or with radiation, whatever. Each of these little oil drops had its own little charge. Now, remember, there's no charge on the plates at this part. So these charged drops just drift down in the air like regular old drops would. He would observe one of these drops falling at its terminal velocity, and the terminal velocity for these drops was relatively low. So, they weren't falling very quickly. And remember, in terminal velocity, that's when it's traveling at constant velocity, when it's falling at constant velocity. But wait a minute, shouldn't it accelerate if it's falling? Well, no. In terminal velocity, that's a situation where the gravitational force is balanced by some upward force. In this situation, if we look at the forces acting on the oil drop, there's a gravitational force downward, but there's a buoyancy force upward and a drag force upward. So in that situation, the buoyancy force and the drag force are balanced by the weight. Now Millikan could measure the terminal velocity with his apparatus, and he had a way to measure the radius of the drops. He also knew the viscosity of the air, and he knew the density of the air. If he knew all those things, well, let's see, gravitational force is mg, the buoyancy force is equal to the density of air times v of the drop times g, and then the drag force is equal to 6 pi times the viscosity of the air times the radius of the drop times the speed of the drop. So with all that information, with what he knew and what he could observe, he could figure out the gravitational force acting on the drop, and therefore get the mass of the drop. All right, so that was the first phase of the experiment. In the second phase of the experiment, he would get the drop to float. And he would do this by placing a charge on the two plates. Really what he did is he created a voltage across the two plates, but that's equivalent to creating a charge on the plates. Either way, he would create an electric field between the two plates and get the drop to just levitate or float at rest between the two plates. Now in that situation, it's no longer falling at terminal velocity. So now, if we think about the forces acting on the little charged oil drop, there's a gravitational force downward, there's still a buoyancy force, but now there's no drag force because it's not moving. Instead, that other upward force is an electric force from the electric field that's between the plates. So, if we now know the mass of the drop from the first part, and we know the buoyancy force, we can figure out the electric force acting on the oil drop. And if we know the electric force acting on the oil drop, and if we know the electric field between the plates, we can get the charge on the drop. So Millikan did this many, many times, and he found the exact charge on many of these drops. It's not an easy thing to do. It took him a long time. It was not experimentally simple. And what he did is he found lots of different charges for these drops. But what he found was interesting. He found that they are all multiples of a single value. They were all multiples of this single value, which we call the fundamental charge or elementary charge. So for example, Let's say he had 5 drops and he measured the charge on these 5 drops. And let's say these are the charges on these drops. Negative 3.2 times 10 to the minus 19. Negative 9.6 times 10 to the minus 19 coulombs. Negative 8 times 10 to the minus 19 coulombs. Negative 6.4 times 10 to the minus 19 coulombs. And negative 4.8 times 10 to the minus 19 coulombs. Well, if you look at these, all of these charges are multiples of the fundamental charge. What that's saying is you can only get multiples of this elementary charge or fundamental charge. And that must be the charge on the electron.